both on the RHIC spin program and also like one TMDs at EIC.
Yeah. So I will try to talk about how to go from RHIC to EIC. For RHIC, I will not cover any kind of the inclusive parton events because we are still not completely sure how and what type of TMDs are related to. And I will not cover the IFF because Anselm will cover that in his talk. So we wanted to be complimentary about these things. So actually, why would you, and we have discussed it yesterday already a bit, why do you care about PP to access TMDs? And I actually think it is absolutely critical for an EIC that you have the information from PP. First of all, you want complementary. QCD has two concepts which lay its foundation, its factorization and universality. And if you truly want to separate interaction-dependent phenomena from intrinsic nuclear properties, you need complementary probes. And they are absolutely critical because if you measure it only in one process, you don't know whether it is actually interaction-dependent or it is an initial property. So you need high precision data from EP, PP, and E plus E minus to actually really have the full complementary and to test these two foundations of QCD. Gluons. So gluons is one of the driving factors of the EIC. We want to study gluons, we want to study their three-dimensional behavior and so on. To access actually gluons directly, PP is absolutely cute because you have core gluon and gluon scattering directly. So the gluon always enters at leading order. And TMD observables and particularly gluon fragmentation functions and gluon linear polarization is something which you measure actually best in PP because with fragmentation, gluon fragmentation in DIS always enters only through the evolution. In DIS, of course, you can have to tag PGF or you measure FL, where you then actually really access the gluon also directly. You have evolution. Evolution is a very active area for TMDs. Proton-proton colliders right now routinely access high Q-square and high PT, much more than the fixed targets experiments. So you can already get a view on what the evolution effects are by looking to this data. And actually, you want to know this because you need some of this information to tune your machine and your experiments actually properly so that you can make measurements at an EIC. So I personally think, and I'm very convinced about this, and if you have heard me talking about RHIC, that hadron collider data is critically, absolutely critical to fully realize the scientific promise of an EIC. It will lay the groundwork for the EIC, both scientifically because you get the complementary probes, but also by actually that you are able, having this knowledge, to define your experimental requirements properly for what you want to measure at an EIC. So if we look at TMDs, that are the measurements by Compass, Hermes, JLab 6, and that is the 12th area for JLab. And that's where we have right now our information for particularly the polarized TMDs. And what we see is all high X and relatively low Q square. If we then put on top of actually what RHIC can do, then you have here actually the X and Q square which are covered by the jets and hadrons inside the jets by the Q square range for 200 and 500 GeV. That is where the W's and C's sit, so really high Q square, and but the same X regions and is covered by CDs right now, which is nice. And then if we go and have our forward upgrades, then you actually come to slightly lower Q square, but still between 10 and 100. So you have a very hard scale. And you go to really forward X, even more forward than what is currently achieved by the fixed target experiments. And the shaded area is the Drell-Young kinematics at RHIC. So RHIC will actually really provide unique kinematics where you can test whether TMDs survive at low X and high Q square, which with the fixed target experiments you cannot right now. So you can constrain the TMDs over a wide range. I showed this already. You have actually different processors available. Processors which have two scales, which are then directly really TMDs and not with three. So like Drell-Young, WC, Dichet, and hadrons in a jet. We have different square root s, which gives you different pt. It's the same xt, so you can actually test evolution, and you can test non-universality of the TMDs like the Sivers function, which you have through the W and C. You have observables as transversity, which we can actually access in two different processes, so we can actually do a check on whether factorization holds by ourselves. One is the IFF, as I said, which Anselm will show. The other one is Hadrons inner chat, and we can test this. And then we have actually observables which are one scale, like the pi 0, gamma, and chat, which are actually testing the twist 3 formalism. Again, we can measure for different square root s, and we can actually test the evolution of this twist 3 function, which to my understanding is at the moment pretty unknown. So we can measure the initial state TMDs through the W and C, the Sivers function. We can look to Gluon-Sivers function in twist 3 and direct photons. And as you all know, of course, the TMDs and this twist 3 are kind of related to each other through these relations. We can look to final state TMDs, like transversity times Collins through this method, and that is what I will also concentrate on in the following, by looking to azimuthal distributions of hadrons inside a chat. We can do a Di-Hadron production to look to the IFF, and we can do the well-known pi plus, pi minus, and pi 0 single spin asymmetries, which probe, for example, this novel twist 3 mechanism in the fragmentation, which I'm sure Daniel will talk about. And again, the fragmentation functions, the TMD ones with the twist 3 ones, are related to each other. So, hadrons in a chat, it's an observable which is more recent. So what you have your chat, and then you pick out a hadron, you have your normal radius of the chat, and just to make it clear, we do a full chat reconstruction in STAR. That means anti-KT, everything which the LHC experiments do as well. So it's not trust axis or something like this, it's full chats. We take one of the hadrons, and then we look to the modulations of these hadrons with respect to this chat axis. You can define, actually by several papers by now, I think one of the original ones was by Bernard, where you define these functions here, where the first observable is collinear, and you can basically measure a fragmentation function, and the second one is like a TMD, because you have this JT, which is the PT of this hadron with respect to this, and which you can then look to TMDs. There have been predictions for this, cross-sections for hadrons in the chat, which are sensitive to the gluon fragmentation, and I will show you what we can do here. There are calculations for 200 and 500 JeV, and also for nuclear dependencies by Sang-Bo and colleagues, where you see actually how the fragmentation, if you look in PA to PP, is predicted to be modified. So here are the first plots, just to give you a little bit of an orientation, what we are probing. So again, here you have your two protons, you have the spin, you have your chat, you have your hadron, and we can be actually multidimensional. And just to give you an idea, all of this is published in this long paper in enormous detail. So here we have the PT as a function of C's, and you have the JT for different PT ranges of the chat as function of J. Then you have the particle chat PT, you have different C ranges, and you see the JT, the same for the C, and so on. So we have actually all the correlations available, and here is what you see actually what we probe in the X range for positive and negative rapidity. That kind of actually dials in what X we probe, and that of course depends on the PT of the chat, and we can go as low as a PT of the chat between 6 and 13.8 GeV. And all of this, the chats of course have been used for all the longitudinal work which we have been doing to determine the gluon polarization. So that is one of the results. So that is actually the pi plus and pi minus inside a chat as functions for C, compared to calculations which have been done by Sang-Bo and colleagues with and without actually also TMD evolution. This data still has a lot of uncertainty, because that was a run which we took in 2011, where we were saying, let's maybe do 500 GeV transverse because of this idea using the W's to do the Sivers sign check. And so this luminosity is limited. It's 22 inverse picobar. With run 17, we have a factor of 14. Just think about this. More luminosity. So the error bars here will shrink enormously by actually a factor 3 and more. So you will get very precise data on this. But it is definitely the first sign that TMDs, like transversity, just 1 second, survive at low X and high Q square. Thank you.
Sorry to interrupt you.
No problem.
There's one thing I don't understand.
Yes.
In this business,
yes.
Did I get correctly that you use TMDs only in the final state and you use a collinear object in the initial state? Is that correct?
Yes.
Yes.
So my question is then, how, if you extract the Collins function business, how can you claim that you are sensitive to the transverse momentum of your initial parton if you have a collinear object? Pardon me?
It doesn't.
It doesn't. Okay, so it's not.
It's a Collins fragmentation function.
So it's not exactly the same Collins mechanism as in series.
It is. It is.
Because in series.
But there you are sensitive to the
no.
PT and integrated the transversity.
Yeah, and here's the PT of the transversity is also integrated over.
No. So that's the magic of this type of fragmentation. So you have two collinear objects. The TMD function is only in the jet. The mechanism is exactly the same up to the first loop. And up to the first loop, at least, it was proven. It's exactly the same as in series.
Yeah, but there is no convolution of transverse momentum. That's what I mean.
So this P.
It's not like in series. So you are not convolving the transverse momentum of an initial parton with the transverse momentum of your final fragmenting parton through the QT.
No. So it's more direct.
Exactly.
Like,
so it's not the same thing that's happening in the
series.
No, it's the same thing in series. It's still same Collins function. Except that in series, it's another correlation between initial transversity, so it's a TMD transversity. And here it's
a normal transversity because transversity survives integrating over PT. So that is the one you use a transversity which basically is integrated over PT in the initial
state. So
in a
sense, it's better to compare this one with the high interference effect.
Yeah. That's what I was.
It is more homogeneous.
That's why I was saying we can do. Yes, exactly. Yeah. Okay. So we have been actually doing the same things also for 200 GeV, and I don't know whether all of you have already seen this data. So you see here in blue, that is a 200 GeV. In red, it's a 500 GeV data, which I just showed you. And now what I show you here is I have two jet PTs, 12 and 31 GeV. I have different C bins, and I plot here versus the JT, which is the PT of the Hadron inside the jet. And actually what is interesting is, so you see here, that is actually where your PT is at small c, your JT is actually much lower, and it moves with C going upwards. So that is actually really interesting. So we see a correlation between the JT and the C in the jets. And actually, what you also see is that the 200 and the 500 GeV data are really consistent, which actually tells you, if you look here, you have a factor of 3 in Q, so a factor of 9 in Q squared, that the evolution effects cannot be so dramatic. And as I said, we have a factor of 14 more statistics. So what do we know about gluon TMDs actually from RHIC? Just to give a small reminder that they are actually really interesting because in the heavy ions and especially in the small system, we have seen all these correlations, which we see also in gold. And one of the explanations actually for this could be that actually linear polarized gluons play a very dominant role to explain actually these correlations in the small system. So actually having gluon TMDs is very interesting also to understand the massive phenomena which we have been seeing. So Phoenix has actually measured very nicely here the muons in the muon arms, where you see here the asymmetries for PP for different, also compared to different models. And actually what you see here is these heavy flavors are kind of sensitive to twist 3, a counterpart of the Sivers, Gluon-Sivers, and 3 gluon correlators. And you see actually that depending on where you are in your kinematics and PT, that you see some effects which are different from 0. Then Phoenix has also kind of measured PP and P gold. That is actually looking to full shape psi, again in the muon arms. You see it here, that actually what is interesting, that there is quite some effect for the P gold, and I think Ralph and Christine should correct me if I'm wrong, that why we see actually this effect in P gold and in PP it's consistent with 0 is not yet fully understood. So we need actually theoretical help to kind of understand that. And we have also P aluminium data to see actually whether they maybe lie in between the PP and the P gold data. And they are still being analyzed. Then actually if we look to chats, that is then a result again from STAR. Here that is single chats, inclusive chats, which probe actually the twist 3 Sivers function. You see here for 500, for 200 GeV. And depending on where you are, you actually probe really quark, gluon, or gluon-gluon kind of interaction. So you are sensitive again to the twist 3 complement of the Sivers function. Then here we have this Collins-like asymmetry of a hadron, again in a jet. Here for the 500 GeV, that is for the 200 GeV data. So that probes actually linear polarized gluons in a polarized proton. That is the first measurement ever, and you see that the data with the uncertainties and the 200 GeV data even more will actually really put a constraint on the theoretical predictions for this, because right now we don't have any kind of data which could give any kind of constraints on this. And what is shown here is actually a prediction by Umberto and colleagues for this observable.
So can you quickly remind me what the difference of this is compared to what we showed?
This one?
No, the one.
That is a different modulation here. So
what you showed.
To both the Collins, yes, exactly. One is a Collins modulation, and that is a Collins-like effect because you have a 2 here in front of the 5. And that is actually the modulation which is sensitive to the linear polarized gluons.
Oh, thank you. Okay.
So then, of course, there is this extremely precise measurement of the single spin asymmetry A sub n at mid-rapidity from Phoenix, which you see here for PP, P aluminium, and P gold. And actually, the same kinematics is used to constrain the gluon spin. And what you see, so you're very sensitive actually to quark gluon and gluon-gluon scattering. And you see this asymmetry is precisely 0 to 10 to the minus 4. Which actually, again, should give a limit on the twist 3 Gluon-Sivers function, and as such also an indirect limit on the Sivers function. So what can you expect from RHIC, taking the 2017 to 2024? So the first one is, we have seen that quite often, that's why I don't want to discuss in more detail about that. That is the A sub n for the W's, W plus, W minus, and the C. With around 17, we can actually improve enormously on the statistics because of the factor of 14. So you see the error bars actually go down to this here in black. And for the C, we can actually even split the points in 3 points in rapidity. And the C is particularly cool because you measure a C, you analyze the asymmetry. It is really easy. There is no what's and what and something about, no Monte Carlo corrections or whatever, and you will nicely get whether there's a sign change or not with these data points. And we hope we come out for something for next EIS to do this. Okay, that is actually the same observables I showed you before, twist 3 Sivers function, the linear polarized gluons, and here actually the Collins, and you see how the uncertainties will go down from what I showed you compared to if we analyze around 17. Then here, that I said already, PP is the best way to measure gluon fragmentation functions. Here is pi plus, pi minus in a chat for different PT bins of the chat, and you see very nice kind of uncertainties to constraints that. We can do that also in PA, and then we can form the ratio. So we can actually look how the gluon fragmentation is modified from going from a proton into a nucleus. And RHIC is the only way where we can do that also for the Collins function. So we can actually really study whether we have a modification of the Collins fragmentation function, so spin effects, if we go from a proton to a nucleus.
Really dumb question. The upper left, is that data or?
No, that is projection. It's based on what we already have. Okay, one thing which I wanted to point out, something which nobody necessarily associates with, we can actually also measure GPDs, and we hope we can measure Wigner functions. We are working with Yoshi on this. So, and what do? We use ultra-peripheral collisions, where you have your one proton or gold nucleus which emits a photon and scatters them. So it's basically the same as photo production in DIS. You produce shape psi, and the asymmetry actually of this shape psi in UPC is directly sensitive to the GPD E if you have your proton transversely polarized for gluon. So here you see actually already a shape psi peak in this, and with around 17 we will have in the order of 1,000 shape psis, and we can bin that in 3 bins in T and see whether we actually see an asymmetry. What is also nice, because we have the Roman pots, we can actually really ensure exclusivity. We don't have to necessarily do just a rapidity gap. And if you do now, instead of producing a shape psi, do 2 Di-Hadrons in the final state, then, and we can do Di-Hadrons. We have shown that for and back and up and down in RHIC very well. Then actually you can kind of do exactly what Yoshi has proposed in looking to the imbalance of the 2 Di-Hadrons, and then you measure the T in the Roman pots, you have the KT, you have the invariant mass, so it gives you Q square, a hard scale basically, and then you can actually have maybe a first look into what happens with Di-Hadrons. And we want to carry that over then and look what is possible at an EIC, but probably STAR will be the first experiment which can have a look into this.
Sorry,
yeah?
Is it Wigner functions or GPDs? Are you accessing Wigner functions?
You know, I always get confused in this exact things between both of them. Maybe it's one of
momentum space GTMD or mixed momentum and configuration data, more or less.
So I measure KT, I measure P, and I measure X because of the rapidity. It's, I think it's Wigner, but as I say, I'm always getting confused about it.
Yeah, so there's no difference.
So,
One object is
okay, we measure something nobody has before measured, and I think it's a cool thing. Whether we call it GTMD or Wigner, we can maybe figure out. So what is also very cool is that we make quite some step forward to have a forward upgrade in STAR, which consists actually, we want to cover the rapidity 2.4 to 4, and that means STAR will have full coverage, tracking and calorimetry from -1 to 4, which is actually really nice. That is nice for looking into saturation, but it's also nice for spin effects, because we can actually take all these TMD measurements now to the forward region and go to even higher or lower X. And the review for this is happening in November, and then hopefully we get to go forward to do this. So just to give you an example, so that is the region which we would cover here, and then that is actually kind of the high rapidity, the statistical precision, which you could look actually in a hadron, in a jet, and then really measure at very high X transversity, and that rate hopefully gives a better constraint on the tensor charge. And I have understood the scalar is important, but I haven't yet understood how to measure it. Okay, so constraining Gluon-Sivers function at a future EIC. We have published this paper where we did a very comprehensive study of what can you actually do. And we confronted the theoretical ideas with experimental reality. And I apologize for the experimental reality in advance because it's sometimes not as easy to measure things. So if you want to do that, you have to take on photon-gluon fusion. You need, as was explained, I don't have to explain this, you need the imbalance between two charmed mesons or two jets and so on. We looked to several final states. We did open charm, we did charged hadron pairs, and we did dijet pairs. And actually what I show here, depending on what the final state is, actually you also probe a different excluon. So which is actually also showing that some of these processes are actually complementary. So what did we do? We used Physia. We used certain beam energy, and I can tell you, you cannot do any of this below 20 on 250 because your cross sections are too low. We used the partonic kinematics flavor information and generated weights for each of the events. Then we pass it through the hadronization, the detector acceptance, and so on. And then we get the single spin asymmetries, which you would see in an experiment. So just the input of the model, the Quark-Sivers functions were the latest extractions here for gluon. We used this one here, but we also used positivity-bound kind of ansatz to do this. You see here the functional forms for UD and so on, which we use synthesizes. And there you see the Gluon-Sivers, and then you see 5% and 10% of the positivity bound. So we wanted really to study what is it actually you can kind of extract if you have certain data. We also made sure that our Monte Carlo ansatz is not BS, so that we can reproduce actually existing data so that our simulation gives the right PT distributions, the right cross-sections. So we compared actually for charm with the H1 data, the unpolarized, and you see an excellent description of the Physia setting with the charm data from charged particles, with the charm data here over a wide range in PT. Then we actually went so far that we also modeled the compass data. So that is the AUT of compass for positive and negative hadrons. And that is actually how well we describe with the model which we are using this asymmetries versus X Bjorken and versus C. So also a very good description of this. So that actually shows that the model also for the Gluon-Sivers, for the Quark-Sivers makes sense, because of course that is what drives actually the compass data. So the Monte Carlo definitely was suited to describe the cross-section. So as such, the uncertainties, statistical uncertainties, and also actually the measured asymmetries for the quarks. So, and then if you do this, then you find actually that there's quite some interesting things going on. So what you see actually is that you have an input asymmetry, and purely by going, so you have the full simulation, and purely the fragmentation process, and also that in your fragmentation you just not only produce hadrons directly like a pion, but you produce rows which then decay. You get an enormous smearing from actually from here, that is the parton level kinematics, and that is what you see in your experiment. And that can be as big, so that is actually for the compass kinematics, so that can be as big as a factor of 5, depending whether it's a pi plus or a pi minus.
So like,
yeah.
Since this is important, I'd like to understand it better. So the full simulation also contains.
So that is a parton. So that is my quark where I put my Sivers function. And then of course I don't detect my quark.
Yeah.
I detect a hadron in my detector. Okay. And if I do this, this hadron goes through fragmentation. It's not just proof, it goes through fragmentation. And I detect one hadron. It might not be the hadron which has a struck quark in it. We don't know this. And also, I don't produce pions only directly. Pions come from rows, from case shorts, from whatever. What is all produced in this fragmentation. and we just look to a pion. And that is another effect which leads to this, leads actually to this smearing from the parton kinematics down to what you see in the detector. So you need actually to understand, and that comes back to very well to the point also from Ralph, you need to understand your fragmentation very well. And you need also to understand what else I produce instead of only a pion and where my pions are coming from. And that actually points to the point, and Hannes always makes, that actually I don't think we can extract high precision extraction for TMDs without a Monte Carlo method. We need really to model this, because it matters quite a bit whether your pion comes from a K-short, a row, and whatever you produce, or it is directly produced. And you see this here because I have done different things. I turned off fragmentation, and I turned off this, basically this Paget 21 means I have no particles like rows and so on in, and then I turned on the fragmentation. And what you see actually, that the resonance decays is the one which, at least in the compass, but I had so many, so I still have, in the compass kinematics, is the one which gives the biggest smearing. Okay, so here you see actually for charm, you see the pion, kaon momenta, you see the PT relations and so on. And for an EIC detector, actually, we have modeled what we think an EIC detector should look like, so actually they are pretty well suited to be seen, so you don't lose a lot. Okay, and then you require a D and a D0 bar. You do 10 inverse femtobarn, and that is your statistical uncertainties you get. That is your asymmetry, which you have in the quark gluon channel, so you don't get for different kind of Q-square bins here, so you don't get, it's extremely clean, as was pointed out by Christian. You basically have no kind of contribution which dilutes this, but you have enormous uncertainties. We also looked into a D0 alone, and what you see actually is that is for 10% positivity, that's what you would measure, maybe. But you get a huge smearing from your original kind of quark to the double, because of course the D0 doesn't give you the full kinematic information.
If I have like a 100 positivity,
100%? Yeah. We haven't done, because we know that all the data we have don't support 100%.
Yeah, I was just thinking about that if the theory can just increase by linearly by.
I think so, yes. Yes, oops, sorry. So then we did the same for hadron pairs, because two high PT hadrons also tax very nicely on PGF, and you can see that here where you are in X-Björken. Then again, here you see actually for 5% positivity bound, the parton levels, and you see the different asymmetries. 5%, the CD1, which is this one model which we used, and then the quark only. Again, you get quite some dilution. Your statistical precision is not so bad, but it's also not too great that, for example, to resolve something like this CD1 for the Gluon. Even more on the Di-Hadrons now as function of X-Björken and for Q-square. So just to give you an idea what you could measure with 10 inverse femtobarn, what X range and how the kind of points are. And you see actually if you want to measure X distribution, you have to integrate quite a bit to get these uncertainties over the Q-square, just to give you a feeling for this. So then we went further, we did Di-jets. So anti-KT, an R of 1, that is the cuts for the jets, which we basically take from things which we have been doing, Brian and so on studies for jets in RHIC. So again, 10 inverse femtobarn. Here you see actually versus X, where your gluon channels and your quark channels are kind of dominating, because of course for Di-jets you can have also QCD Compton for gluon in the final state, which causes quark jets. And you see that for two different Q-square bins. So that is the low Q-square bin 1 to 5 and then 10 to 20. Here you see the parton asymmetry for 5% positivity bound. You see actually that the smearing for the Di-Hadrons is much less, and for the Di-Hadrons, you see here some actually the corresponding. You see the other CDs case, and you see how much actually comes from the quarks. Anti-KT, yes, exactly. So here you see actually then how the asymmetry would look for different X spins as function of Q square. The same for one Q square bin as function of X. And you see where actually the quarks come in, it is at this higher X. And you here see how well you actually reconstruct the parton kinematics by looking from the two Di-Jets, and you see the asymmetry as the reconstructed parton direction. And you see here again the quark contribution is actually relatively minimal. Then we have done how actually the smearing happens. So here you see the parton level. Then you see what you get if you turn off fragmentation and the decay. And that is actually if you have all on. So you see you also for the Di-Jets you have quite a bit of smearing versus Q square, the same versus X. And we also studied in the paper, and I forgot to include that plot, whether if we change the R of the jet from 1 to 0.8 and so on, and there's very little dependence on the R of the jet, because you basically need the axis of the jets very well reconstructed to do this. So in summary, I think RHIC, forward and mid-rapidity PPA program addressing very fundamental questions in QCD. The Hadron Collider data are crucial to test all aspects of the TMDs. If you really want to understand them in full glory, you need the data as well. The Gluon-TMDs at an EIC are a good example that it is critical, I think, to confront ideas with measurement reality, because if you do that, then you see that suddenly, unfortunately, because you have to measure two charm mesons in a detector, that you actually kind of get pretty big error bars. So all in all, the RHIC PPA program and the EIC program are uniquely tied together by universality, factorization, evolution, and that you want to inform actually in the same kinematics, and RHIC has the same kinematics as the EIC. You want to inform your physics program at the EIC with the sizes of the effect so that you can plan your machine properly. Okay, thank you.